And is the screen visible to you? I have shared a OneNote screen. Is it visible to you?
Yes, sir.
Okay. So sorry for the inconvenience. Before that, let me introduce myself. I am Sobi, one of the research scholar for IT Madras. Right now, I am doing a PhD in topology under Dr. Ramesh Kasalingam at IT Madras, and right now I'm in third year. So in this semester, in this points of topology course, I am the TA of this course for the entire semester, and the main goal of this live session of there are okay sorry so there are 24 live session 24 sorry there will be 13 live session for this course in the entire semester, and the main purpose of these sessions are to solve problems, solving assignments and all. And of course, if you have any doubt, you can ask me. And it is always not possible to solve the problem immediately, but if you can ask me on the next session, or I can solve the problem by email or by the discussion forum. So, okay, so that's all. So, okay, so I have gone through the Sastry sets, lecture notes, and assignments that he has uploaded on the NPTEL website. So right now I've decided to start with the compactness because he has started compactness separation action. So first compactness comes, then the separation actions comes. So today we shall start with the compactness. Okay. So before starting this, let me know whether you have done the topology one course or not.
Yes, sir. So I have done that course.
Okay. So, just I want to know one thing that in the topology one course, have you? I mean, so in topology one course, so what are the topics you have studied?
So basic, how we define basic topological spaces. Then we generated new topological spaces using different operations, and we studied many examples of topological spaces. We did connectedness, compactness, large properties, small properties, and I think we did. Actually, I did this course last like last year in 2022.
Okay, so
So
through NPTEL or through college?
no, on NPTL only.
Okay, right, got it. Right now you are doing undergraduation, post graduation.
No, sir, I'm teaching.
Okay, okay. So let's start. Okay. So before starting these things, let me know, do you have any question already in your mind or anything like that?
So actually, the first week of this course is somewhat related to functional analysis, and so I have doubt only in that functional analysis portion. So today, are we going to do this functional analysis portion
Hmm.
or something else?
Okay, so you can do one thing. Whatever doubt is, you can post on the discussion forum,
Okay.
and I will solve it as much as I can. But I mean, it may take 2 3 days, but I will solve it as much as I can. Okay.
Okay, sir. Okay.
And one more thing is that today I have started the compactness because actually from this onwards topology starts. Okay, I mean those are out of the. I mean functionality directly is not inside the topology. That's why I have started the compactness. Okay, so functionality I will do, but after 3 or 4 classes from the when the core topology portion finished, then functionality portion. Okay,
Okay. Fine, sir. Fine.
yeah. So just I want to know one thing. So you must have idea of the compactness already, right? Or these are totally new to you?
No, sir. I have idea.
Okay. And also one more thing, if in between you have any doubt or you type something in the chat box, it is not may not be visible from my side. So in that time, unmute yourself and please tell. Okay.
Okay.
So today let's start the compactness. Okay. So first, compactness starts with something called that known as cover. So what does a cover mean? So let X be a topological space, then and then a collection of subsets of capital X, call it U, will be said to be an. Okay, so first I will give the definition, then I will give the examples. So, oh, so for this side will be an open cover if um, X is equal to union U alpha, U alpha belongs to Q, where U alphas are open subset of X. So, according to this definition, what does a cover mean? So, cover or to be specific, it is actually known as open cover. It is an open cover. So suppose we have some space capital X topological space, okay, and suppose we have some collection of open sets such that their union covers the whole of X. Then this collection U alpha is called an open cover of X. Okay, so this is definition. So I mean, of course. So what are some possible examples? Suppose consider topological space X equal to R. Sorry. So X equal to R. Then so we can cover. So now we want to cover a real line with some open subspaces. How we can do that? So this is 0. So we can do like that: -1 1, -2 2, -3 3. So U is a collection of UNs where each UN is of the form -1 by n. Sorry. So where each UN is of the form -n, n. So clearly this U, this collection of opens of UN, this covers whole of R. Okay. And of course, so I mean, so from this construction, it is clear that open cover not necessarily unique. So for example, if we consider X equal to R again, and um, if we consider minus infinity comma 0 union -1 comma 1 union 0 comma 2 union 0 comma 3 union 0.3. This 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 each of this, I mean, collection of all these open subsets also form a cover. So that's why open cover of a given space not necessarily unique. Okay, so this is the first thing. Now the sorry, yeah, okay, now I think you can see this. Sorry. So what is the last example? Last example, what we have some X equal to capital R, and the open sets are minus infinity comma 0, minus infinity comma 0, -1 comma 1, 0 comma 2, 0 comma 3, 0 comma infinity. This collection forms an open cover of real line. In this, so we can construct many possible open covers and of any given topological space. Okay. Now let's go to the definition of compactness. So definition goes as follows. Let X be a topological space. Let X be a let X be a topological space. Then X is said to be compact if every open cover of capital X has finite subcover. So what the definition tells? X is a topological space. X is to be compact if every open cover of X has a finite subcover. What does that mean? So suppose U is an open cover of capital X, some index alpha. Suppose this is an open cover of capital X. Now by finite subcover, we mean, so by finite subcover we mean finite number of alpha 1, alpha 2, alpha n's such that X can be written as union of U alpha I is equal to 1 to n. So means instead of considering all possible open subspace of the open cover, if we consider a finite amount of open subspaces of that open cover, then those finite open subspaces also cover the capital X. So if such a situation occurs, then X is said to be a compact space. Okay. So the definition goes as follows: space is compact if every open cover has a finite subcover. Yeah. So and what does by finite subcover mean? So U is equal to, I mean, okay, so suppose U is equal to U alpha be an open cover of capital X. Then a finite subcover, we mean a finite collection of alpha 1, alpha 2, alpha n, so that X equal to union of U alpha I is equal to 1 to n. That is finite subcollection of that open cover over the whole of capital X. Okay. So this is what we mean by compact subspaces. Okay. Now, so let's see some examples and also non-examples. Okay. So let's see some, suppose some non-examples first. Suppose X equal to R, then R is not compact with usual topology. So, so this is what we need to do. The R is not compact with usual topology. So for this, what we need to do? So basically, we need to show that if we consider, so what is the definite compactness? Definite compactness is like every open cover has a finite subcover, right? Now we need to show that R is not compact. So this is what we need to do. We need to show that if we consider any open cover of capital R, sorry, any open cover of the real line, then this cannot have finite subcover for any open cover. So so let so let U be an open cover of R. Okay. So mm, sorry, let me make myself correct. So by compactness we mean that every open cover finite subcover, right? Now if we want to show that real line is not compact, means what? We need to find out at least one open cover of real line which does not admit a finite subcover, correct? So for this, first we need to choose some open cover which cannot admit a finite subcover possibly. Okay. So for this, what type of open cover we can choose? Could you please tell? So what open cover we can choose of our real line so that it cannot admit a finite subcover.
So the one which you took in the starting, like open interval minus n to n, that will also.
So this one, right?
Yes, sir.
Mm, mm, mm. Okay, correct. Good. So just writing the argument shortly. Take u to be minus infinity 0 union minus 1 comma 1 minus 1 comma 1 union 0 comma 2 union 0 comma 3 union. This open cover cannot admit finite subcover. So this is one. So now, real line is not compact. So this is done. So let's consider another example. Hmm. So 0 comma open 0 comma close 1 is not compact with visual logo. So this is need to. So for this same way also we need to construct an open cover of open 0 closed 1 which does not admit a finite subcover. So for this what the open cover we can choose? Can you please tell?
So open interval 1 by n to 1, closed at 1
Hmm. Okay.
from n plus, where n can take value from 2 to infinity.
Uh, yeah. Hmm. Okay. So this cannot admit finite subcover. So the argument goes as follows: if we'll call this given, if it admits finite subcover, then there exists n1, n2, nk such that open 0 close 1 is made of 1 by n1 comma 1 union 1 by nk comma 1. So this is equal to open it over 1 by n comma m, where m is equal to max of n1 into m. Okay. So these are equal. So this is not possible. So so 0 comma 1 is not compact. Okay. So this is the another example. Right. Now So this is one example. So now, okay. So this is regarding compactness of a given big space. I mean this is a compactness of a space. Now the same argument, the same definition can be given as the compactness of a subspace also. Okay. Suppose, so let y be a subspace of x. Suppose y be a subspace of x. Then y is compact if and only if for any collection of u alphas with y subspace of union u alpha, there exists finite number of alphas such that y sub of union of u alpha I is equal to 1. So basically the same definition is the compact subspace. Instead, here the one point is that this any collection u alpha, these are open sets, so these are open subspace of capital S. This is one thing you need to observe. In general, the definition follows like that: any opens with any set which are open in capital Y will satisfy the finite super property. But say when we are considering these u alphas to be open source capital X, then we need to consider Y is subspace of the union, not just equal. Okay, so this is one thing we need to consider while working with the compact subspaces. Okay, now um, so now next there are two important properties of compact subspace, compact spaces. So the first theorem is that every closed subspace of a compact space is compact. Okay. So the first thing, every closed subspace is compact is compact. So how to do? So for that, so suppose a subspace of X be closed and let X be compact. So we need to show that capital A is also compact. So for that, what I need to do? So let A be subspace the union of U alphas. Okay. Now, mm, since A closed, so X minus E is open. X minus A is open. Okay. So this collection U alpha union X minus A, this is an open cover of capital X. Now X compact. So it has finite subcover. So u alpha I is equal to 1 to n union x minus capital A. This thing covers x. So this implies what? A is a subset of union of u alpha I is equal to 1 to n. So this implies A is compact. So this tells that closed as a compact space is always compact. Okay. And yeah, okay. So now the next theorem is as follows. So till now, do you have any question or any doubt?
No, sir.
Okay. So hmm, so um, the next theorem is as follows. Theorem is like every compact subspace of a Hausdorff space is closed. This is the theorem. Compact subspace of a Hausdorff space is closed. So by the way, the definition of Hausdorff goes as follows. So X is a space, and suppose we are taking 2 points A and B belongs to X, which are not same. By Hausdorffness, we mean by Hausdorffness, we mean that there exist two different open sets containing A and B separately, so that their intersection is also empty. This is what we mean by Hausdorffness. Okay. Now, so definition. So the proof is goes as follows. So suppose X be an Hausdorff space. Okay. And let A be a subspace. Not only subspace, it is a compact subspace. Maybe a compact subspace. We need to show A is closed. So for that, what we need to do? We need, so it is equivalent to showing X minus A is open. Okay. Now, so X minus A is open. So So choose a point
So
x
we'll
naught.
fix them.
Yeah, please.
Yes.
Yeah, tell me.
So I was just telling you how we'll do it. We'll fix the point in x minus a,
Mm-hmm.
and then corresponding to every point in a, that fixed point will not be equal to any point of it. Then we'll use
Wait,
Hausdorff-ness.
wait. Could you please repeat again?
We'll fix one point in x minus a.
Yes,
No, outside x
yes,
minus a.
outside. Yes,
Now this x naught, it is not equal to any point inside it. So
yes,
now
correct.
we can use Hausdorff-ness
Uh,
to cover
hmm,
a,
hmm.
and uh, we'll get all many neighborhood of x naught.
Yes,
But
correct.
uh, since A is compact, so A will have a finite subcover.
Hmm,
So corresponding to that, taking intersection, we can make a neighborhood of x naught,
correct.
which will be separate from this A.
Correct, correct. Right. Very good. Okay. So basically, we're saying that since x naught is outside of x my capital A, so for each point inside capital A, we shall get open balls containing little x and the little a. Then we can take the intersection of the all open sets at x naught, and we can take the union of all open sets at different points of capital A. Then that will serve as an open set, right?
Yes, sir.
Yeah, good. Yeah. Well, but I need to write the proof actually, because this has to be uploaded by Integral Polish to YouTube. So that's why I need to write the full proof actually. Okay. So let me be. So x naught is a point in x. So if so for each a belongs to a, there is an open set ua containing a, and there is open set va containing x naught, such that ua intersection va empty. Now put u is equal to union of ua, a belongs to a, and put v is equal to intersection va, a belongs to a. So clearly u intersection v empty, and of course u contains capital A. Okay, and
No, sir. Uh, First, we'll cover A using these UA balls, all the UA. So U is an cover of A, but A is compact, so it will have a finite subcover.
yeah,
Because otherwise V will not make sense. Infinite intersection of open balls cannot be open, no?
correct. Good assumption. Correct. Very good. So using a union UH, now it will have finite subcover. Thank you, weather. Finite subcover. So finite, I mean, this thing contains capital A and finite subcover. So A is contained of union of UAI, I is equal to 1 to n. This is one thing. And then define V is equal to the section VAI, I is equal to 1 to n. And this thing contains little x naught, and this is an open set of course. So x naught belongs to V and subset of x minus n. So this is the thing you was trying to say, right? Okay. So let's go to the next theorem. What's that? Yeah. So now the last so according so the last theorem can be extended in the following manner. Uh, hmm. So there is a lemma. This lemma goes as follows. Let Y be compact subspace of a Hausdorff space capital X, and X naught does not belong to Y. Then there exist open sets U and V of X containing X naught and Y respectively. So basically what this is saying, that X is a space and Y is a compact subspace, and X is a point that we will open set U and open set V containing Y such that they are same. And this is basically something which we integrate from the previous proof. That is, U is our, this is our open set, and this is our open set containing X naught, and this V is outside of U, and also this V intersection U also empty by choice. I mean, by the choice we have taken the open set. So this is the lemma. Okay. So for solving problem, this lemma is actually worth it to note down. So after this lemma, there is one important thing which tells that continuous image of a compact set is compact. Okay. Sorry. Yeah. So the theorem is that image of,
So sorry to interrupt you. So can you
yeah,
repeat this,
yeah, yeah,
or just can you just show the line?
yeah. So the lemma goes as follows. Suppose Y is a compact subspace of Hausdorff's capital X, and suppose X naught is a point outside capital Y. Then we can get an open set U and V containing little x naught and capital Y, uh, respectively. Sorry, I mistake, such that U intersection V is equal to M. Sorry, they did not intersect. That is the thing. And this lemma comes from the previous part of the theorem. Namely, here we have C, and here this portion is U, and the way we have taken U and V, so they are of course intersection M. So that's why this lemma.
Okay. Thank
So now the next theorem goes as follows. This thing tells that image of a continuous, I mean under continuous mode, image of a compact space is compact. Image of a compact space under continuous mode is compact. Okay. So how to put this? So proof is very straightforward. Let F x to y be continuous. Map. Okay. Now let x be compact. So now we need to show that y is compact. So how to do? So let u alpha be an open cover of y. Okay. So this means what? That is y is equal to union of u alpha. So this implies what? This implies f inverse y is equal to union of alpha f inverse u alpha. So that is x equal to union alpha f inverse u alpha. Now since f is continuous, map is continuous, so Each of these things are open. Why open? Since since F is continuous. So this tells this collection F inverse U alpha is an open cover of capital X. Now X compact. So this admits this F inverse of U alpha, this collection, this admits finite subcover, that is X equal to F inverse U alpha is equal to 1 to F inverse U alpha. Okay. So now this implies what? Fx is equal to union of U alpha I. So this tells that this. So this tells what? This tells U alpha I is a finite subcover of f of x. So this tells that continuous image of an compact space is also always compact. Okay. So this is a thing. Okay, so I shall back the 2 minutes. বলো বলো কেন হুম 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 हाँ अच्छा हाँ हम्म 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 ठीक है बुझতে পেরেছি हाँ 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 হুম ঠিক আছে ঠিক আছে হ্যাঁ হ্যাঁ ঠিক আছে হুম yeah okay so so the last theorem was what was yeah continuous image of compact plus compact okay so this is a theorem so till now do you have any question or any doubt
No, sir.
okay so so now the next theorem is actually rather a result, but anyway, it can be considered theorem. Okay. So the thing is, this I mean the result which we are going to see from the theorem is actually very useful in order to determine whether some given map is a homeomorphism or not. Okay. By the way, a map is not. By the way, so what is the definition of homeomorphism? Listen.
So, a map from X to Y,
Hmm.
which is bijection, continuous, and inverse is also continuous.
Yeah. Okay. Okay. So in general, it is not always possible to check the inverse is continuous or not. It is sometimes it is also difficult. Okay, and sometimes Instead of checking inverse is continuous, it is same as saying that a map is open map or closed map. Okay. So directly it is always not possible to check. So this following theorem is actually a tool for checking whether given map is an homeomorphism or not. Okay, I mean this is one of the tools. This is not a criteria. So the theorem goes as follows. So let f x to y be a bijective continuous function, and if x is compact and y is Hausdorff, then f is a homeomorphism. So the statement goes as follows. Suppose f of x to y be a bijective continuous function. Now, if x is compact and y is Hausdorff, then then f is a homeomorphism. So this is a theorem. So what is the proof for that? So the proof goes as follows. So basically, in order to check homeomorphism, what you need to check it is f continuous, if it is continuous, if it is bijective or not. But point is here already f continuous bijective. We already need to check that f inverse is continuous or not. Now, if inverse is continuous or not, it is same as saying that if it is an open map or closed map, right? If inverse is continuous, it is equivalently if inverse open or closed map. Same thing. So now we shall check that. Sorry, if is an open. We shall check that if is an open map closed map. Okay. So for that, what we need to check? So let f be closed in capital X. So what about f of f? Okay. Now since f is closed and x compact, so these two things implies closed subspace of a compact space is always also compact. So these two together implies f is compact. Okay. So this implies f of f is compact since f is continuous. But the codomain y is Hausdorff. Y is Hausdorff. So this implies f of f is closed because compact subspace of a Hausdorff is closed. So that's why f of is closed subspace y. So we have started with a closed subspace of x, and finally f of is closed subspace y. So this implies what? This implies f is a closed map, right? So this f is a closed map. So this is the thing. So that's why if it's a closed map, this is what we need to show. This implies what? This implies f inverse is continuous too.
Just in lectures, sir usually call this compactness,
Hmm.
I think, smallness property and Hausdorff largeness property. I always get confused. Why compactness is smallness or largeness property? Hausdorff is largeness,
Okay, so
or it may be the otherwise also.
so no, compactness is not the smallness property. It is written like compactness and smallness axials, right? It was written like that, right? If I'm not wrong. Okay, let me check. 1 minute. So It was written like compactness and separation axiom, right? The smallness property is also there, but where it is written, but I mean the anyway. The point is that compactness is not a smallness property. Compactness is a universal property. Okay, the smallness or largeness, these type of words are applicable on those properties which depends on locally. I mean, suppose local compactness means if we take any point and if we take a neighborhood, then that neighborhood contains a compact subspace or no. Those type of thing where some neighborhood things are involved, those type of properties are known as smallness properties. Okay, and largeness means those are universally defined. It has nothing to do with the neighborhood and all. Okay. So that's the compactness is a largeness property. Okay. And Shepard's axiom is a smallness property because either countable axiom is a smallest property because either first countable or second countable, those definitions and those properties are consist only, I mean plays only with the open balls, open sets. Okay, so and same and yeah, and the same goes separation axiom because the whatever the separation axiom 4 or 5 axioms are there, all of those involve only or neighborhoods. They are, those has nothing universal. So those are, that's why called as smallish axiom. Okay, the smallest means only neighborhood level these are defined. That's a small. Compactness is not a smallest. Compactness is not a smallest property. Okay, so yeah, so okay, so this tells that so what the last theorem tells. So basically, the last theorem tells that if f is um, if is a bijective continuous function and if x is compact White Hausdorff, then f is a homeomorphism. Okay. So this is one thing one can keep in mind. For example, an example also can be given. Why this is useful in order to do this. So we can define f to be close 0 1 union 2 3 2 close 0 2. How it is defined? X goes to x when x belongs to 0 comma 1 and goes to x minus 1, x belongs to 2 comma 3. Okay, so first of all, of course, this is continuous. Sorry, I mean this is not a homomorphism anyway, but this is at least a closed one. Okay, so this is continuous anyway. Now this portion, this left side is compact, this right side is Hausdorff. So by this theorem, this map F is closed. So that's why this theorem is actually pretty much useful. It can help us to determine the something is compact, something is closed map or not. Okay. While solving problems, we can see that many applications of this thing. Okay. Now, okay. So after this, there is a important theorem. The statement of theorem goes as follows. Right now, we are not getting into the proof of this theorem. Firstly, we shall try to use the theorem when solving the exercise. Proof can be done that way. Theorem is that, like in connectedness, I mean, topology 1 course in connectedness, you might have seen that might have seen that Cartesian product of quantized space is connected, right? So same thing, compact product of compact space is also compact. Product of compact spaces is also compact. finite and infinite. So finite product or infinite product compact species is compact. So this is the theorem. But the proof is really difficult. So right now we are not using the proof. So that's why close 0 1 square. Sorry, I mean close 0 1 close 0 1 not compact. So these are the small application for that. Okay. So okay. So let's okay actually the after 2 minutes. Okay. So next thing goes as follows. So so now we are in the position to okay. So the last theorem is just follow the product compact spaces. Sorry. So product compact space is also compact. Okay. Finite product, infinite product, whatever it is. So now we are in the position to solve some exercise problems. So let's start. Okay. So before starting, let me know, do you have any question or any doubt? Do you have any question or doubt? Okay.
No, sir.
Okay. So let's start some problem. So the first problem goes as follows. Let tau and tau dash be two topologies on capital X, and let tau dash contains tau. Then question is, what does compactness of X under one of these topologies imply compactness under R? So this is the question. The question goes as follows. So we have some two topologies tau and tau dash on a given space capital X. Now question is, if tau dash is compact, then from this we can say that tau is compact, and reversely the question is that if tau is compact, then from this can you say that tau dash is compact. So this is the thing. Okay. So 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 okay. So I will explain what if you have any idea in mind, please tell me. You can take your time.
If if X will be compact and under this tau prime, then it'll always be compact under tau. No?
So you're saying that if the big one, the tau prime is compact, then you are saying that tau is compact, right? Correct? Yes or no? I mean, you are saying that tau, if tau is compact, then sorry, if tau prime is compact, then tau is compact, right? This is what you are saying, correct?
Yes, sir.
Yeah, yeah, that's a good argument because if you then open set of tau is also open with tau, so yeah, so finite support condition is valid here. That's good. So whatever converse, so tau prime compact implies tau compact. So whatever converts, and of course, intuitively converts not true. So what is the counter example for that? Think about it. Take a plan. Let me think also. So could you please make an counterexample? So basically, what the counterexample should be as follows: like the tau prime is not compact, but tau is compact. So what type of example we choose? So if we check, so first for this first we need to consider at least a non-compact space, correct? Mm, so tell me the real line with discrete topology. This thing is not compact, right?
Yes, sir.
Hmm. And real line with discrete topology is finest topology. Means this means what? This means every topology is contained in the discrete topology. So of course now R with usual topology, R with usual is contained R with discrete topology. Sorry, R usual is sorry, let me take myself correct. So R with uh, in discrete topology. So do you know what is indiscrete topology?
Yes, sir. Only the entire set and empty.
Yeah, correct. So that is always compact and discrete is always not compact. So that's why. So this is the counter example. Left side is not compact, right side is not compact. Okay. So this is the exercise. So the second exercise goes as follows. So let x be one. Sorry, compact plus house top under both topologies tau and tau. Then then show that either tau is equal to tau dash or they are not they are not so they are not comparable. So what is this? So we have some compact house of space and under so we along with two topologies tau and tau dash. Now the question is that either do those two topologies equal or they are not comparable. So think about how to attack this problem. Take your time.
So we
So
can use exercise one also, no?
sorry, x.
We can use exercise one. Can we use exercise 1?
I mean, you need to. I mean, yes, you can use. So from this question, is it clear that what you need to prove? So you need to prove that if suppose tau dash subset of tau, then you need to prove that tau is equal to tau. This is what you actually need to prove, right?
Tau is contained in tau prime.
Yeah, I mean, if one is contained in other, then you need to show that both are equal. This is what you need to prove.
Yes,
Understand?
sir.
Yeah.
Yes,
Think
sir.
about it. Yeah, think about it. So for this one hint I am giving is that so there was one theorem, namely this, that um, this one, what is it? So this theorem. So if f(x to y) be a bijective and continuous function, and if x is compact, y is Hausdorff, then f is a homeomorphism. Okay. So you need to use this theorem in order to solve that exercise somehow. Now think about it, how you can give a map first, and then so it is already given that tau is subset of tau dash. You assume then you need to show that tau is tau dash.
Ident-
So you need to construct a map first, right? So think about it, which map you can construct
The identity map
from where to where.
from X to X.
No, no, x to x, that I understand, but which topology to which topology? So you are assuming that tau is subset of tau dash, right? Is the assumption correct?
Yes,
Okay, now which map? So x to x, that I understand, but x which topology? Both sides, of course, both sides you need to different topology, but which topology in which side? So that the ideal
so
map will be continuous.
compact in the domain side and Hausdorff on the range side.
No, no, both are compact and Hausdorff, right? Both are compact to
Okay.
Hausdorff. Only the assumption is that tau is subset of tau dash. Now you
Tau
need to
prime or
decide which one should be domain side and which one should be codomain side, so the ideal becomes continuous.
so to need continuity, I, there should be lesser number of open sets in the range.
No, I mean,
So
okay,
I
okay,
tau
so let's see how to look into it. So there are two possibilities: either x tau to x tau dash, or x tau dash to x tau. One of them is obviously continuous, right? With the both identity, correct? Correct. One of them is continuous. Now we need to check which one is continuous, right?
yes, sir.
So if we consider the first one, if you take if we take u to be an open subset of tau dash, and then I inverse u is what? I inverse u is equal to u, but tau dash is bigger, tau is smaller, right? So this u may not lie inside tau. But if you consider second situation, if u belongs to an u is an open set on the codomain, then I inverse u, which is u, and this also belongs to tau dash because tau is subset of tau dash. So this second portion, I mean the tau dash, I mean the bigger side lies on the left. So x tau dash to x tau, I did remember this is a continuous map. This is the first thing, right? Understand?
Yes, sir.
Yeah. Now under this setup, both continuous house of all these. Now under this situation, I am using that theorem. Try to show that um, these are equal. Think about it. Take your time.
So this is a homeomorphism now, no? Because it's a bijection already.
Yes, it is correct. It's a bijection, so it is a homomorphism and identity. So that's why tau is equal to tau. That's correct. Very good. So yeah, so that's the exact. So this is one application of that theorem. Direct application. Okay. So now, So first tell me, do you, so of course, so please tell me, what does it mean by cofinite topology?
So one last question.
Yeah,
In exercise two, there were two cases, no? Either they are same or they are not comparable. So
yes, correct.
when will be the case when they will not be comparable?
No, no, they are not. I mean, we need to show that either they're equal or they are not comparable. Comparable means
Okay.
what? Comparable means either tau subset of tau dash or tau dash subset of tau. But the point is that if they are compatible, then they are equal. So that's why it is written like either they are equal or they are not compatible. So that's why if we assume they are compatible, so then we need to show that they are equal. You understand?
Okay. Yes, sir. Thank you.
So okay, now tell me the definition of cofinite topology for an infinite set.
So if X is an infinite set, then U is open in X if and only if its complement is finite, and we have to take the empty set also.
Hmm. Good. So the exercise was as follows. Let X be an infinite set with cofinite topology. Then show that X is compact. X is infinite set is cofinite topology. Now we need to show that X is compact. So first try to do it by yourself. Take your time. It is not directly coming, but it is not difficult also. Think about it, take your time. Whatever the idea is coming in your mind, please tell me.
Sir, because if I take only one open set in X, then its complement will have only finitely many elements. So to
Hmm.
cover X, I just need actually one open set, and then to cover remaining like finite number of element, I can choose that many subsets. So every open cover will have finite subcover, so it will be compact.
Yeah, very good, very good. Okay, so let me down on the proof here. So let U be an open cover of capital X. So these are U alphas. Hmm. So now if we take an alpha naught belongs to the index set comma, then this implies x minus u alpha naught is finite. Okay. So suppose this thing containing x1, x2, x3, xn, and then suppose xi belongs to u alpha I. So this implies x is equal to u alpha naught, u alpha 1 union u alpha n. So that's why x is compact. Very good. So it is actually very interesting that in cofinite topology, infinite set is compact. So of course you know the definition of co-countable topology, right?
Yes, sir.
So unlike cofinite topology, the same situation does not hold true for the co-countable topology. That is, X is an uncountable set. Sorry, with co-countable topology. Then X never for any given space X, countable set co-countable topology, X cannot be compact. So for this, you need to come up with some open cover, right? Think about it. Think about how to get an open cover. So while thinking, you can also choose real line instead of arbitrary characters. Okay.
So can we take X to be real line and
Just for getting the intuition, getting the idea, you can take X to be real number also.
okay. So co-countable topology.
Yeah. You need to first come up with an open cover which possibly cannot admit a finite subcover, at least intuitively.
So X minus, if I'll take open set of the type X minus Qi, where Qi is the ith rational.
Yeah, so you're taking X equal to R. And what are the open sets you are taking?
R, sorry, R minus,
Hmm.
I'm not sure, R
That's fine.
minus, suppose I'll subtract the first rational, but no, there is the,
Sorry, first rational. Okay. Then this is one open
no,
set, right?
yes, sir, but
Okay.
I think it is not correct.
No, this is one open set. So what about other open sets? No, you are
But
going in the right direction. You just told me that's one open set of the open cover. So what are the other open sets?
okay, now if I take,
Hmm.
but if I'll make it R comma R2, like from real, if I'll subtract R1 comma R2, then R1 will not be anywhere. It will not be cover of
So
X.
instead, so basically you choose the enumeration of the rationals and then you
Yes,
are subtracting one by one. So instead of subtracting a finite thing, you can subtract an countable thing also, right? Correct.
yes, 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 yes.
So think in that way. I mean, instead of writing r minus r1, you can write r minus r1, r2, r3, dot dot dot, r minus r2, r3, r4, dot dot dot, something like that. Think about it. You're in the right direction. I mean, you need to take the advantage of countability. So, but you are taking the advantage of finiteness. So you need to take the
Okay,
somehow
okay, sir,
use
okay.
the countability thing. So instead of taking the complement R1 and R1 comma 2, if you take this like R minus R1 R2 R3 dot 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 R minus R2 R3 R4 dot dot dot, then what will happen?
Okay, so then it will cover R, but we cannot have a finite subcover, so not compact.
So yeah, so now this, yes, correct. So if we implement the same argument in arbitrary uncountable space, then what you will do? So the, I mean, so you have took some rational enumeration, but if you choose some arbitrary uncountable space, then instead of choosing R1, R2, R3, what you need to do in for arbitrary uncountable space? Think about it. What is the analogous thing of this enumeration in arbitrary uncountable
So a
space?
sequence, we can subtract the sequence.
Correct. We can consider countable subsets and we can subtract, right?
Yes, sir.
So basically, this looks like x minus x1, x2, x3. Dot dot. This is u1, u2 is equal to x minus x2, x3, x4. Dot dot dot. Similarly, un is equal to x minus xn plus 1, xn plus 2. Dot dot dot. So these ui's full x, but of course finite. But if we but if x is equal to union of u n I is equal to 1 to k, then this will be x minus x n k plus 1 comma x n k plus 1 plus 1 dot dot dot, which is not equal to full of x. So that's why any uncountable set cannot be compact under co-countable topology. So this is the argument. Do you understand?
Yes, sir.
Good. So now the next question goes as follows. Yeah. So the next question goes as follows, namely, uh, so finite union of compact subspaces of X is also compact. Finite union of compact subspace of X is also compact. So, so tell me how to attain this problem.
So we can define y1, y2, yn to be compact subspaces of X. Then we can take their union, we'll call it capital Y, and then we'll cover capital Y with like the cover
Mhm.
of capital Y will be of the sets open in X. But then that cover will be a cover of each subspace. So
Yes.
corresponding to each subspace,
Mhm.
it will have a finite subcover.
Yes, correct. Very good. Very good. Very good. Understood. Okay. So the next question is as follows that are okay. So next question seems interesting. The question is that let A and B be disjoint compact subspace of a host with capital X. Okay. Show that show that if show that there exist disjoint open sets U and V containing A and B respectively. So theorem statement goes as follows: A and B are disjoint compact subspaces of house with capital X. We need to show that there is disjoint opens U and V containing A and B respectively. So basically, for this, you need to use the following theorem. So this is the hint. What is theorem? So, huh. So this is the lemma, this which is needed to be used. That is y compact also housed space and x naught is a point outside y. We can get open set u and v containing inside the y. Just join. You need to use this lemma in order to solve this problem. Now take your time, think about it, and tell me how to solve this problem. Okay.
So it will be similar to what we did earlier. For it's like earlier we separated a point and a
Yes.
compact space. Sorry, sorry.
Yeah.
Using open. Sorry.
Yeah, I understood what I was trying to say. Basically, the in that lemma there is some point, so we can take we can consider each point of view, and for each point of view, we can consider open set containing that point, and we can also get an open set containing capital V. Now, for the open sets that which are getting against each point of view, we need to take union. Then we will finite things. Sorry, I mean for capital and capital is for V and B. Then for finite set we can take the union, and for capital V we can get finite open sets. We need an intersection. So those will serve an U and V, right? Correct. So basically,
Yes, sir.
okay. So let me write. So, so take A belongs to A. So this is what A does not belongs to B. So there exists an open set UA containing A, VA containing B, such that UA intersection VA empty. Now this collection UAA belongs to A. This thing covers A. So it admits a finite subcover. So union of I is equal to 1 to n contains capital A. So put U is equal to union of UA I is equal to 1 to n, and V is equal to intersection VA I is equal to 1 to n. So then of course U and V empty, and U contains capital A, V contains capital. So these U and V serve the job, right? Oh, so mm, what is so let next question goes as follows. Okay, so before going to the next thing, so we have a following theorem. Okay? We shall prove the theorem in the next session. For the timing, let's um, get into the statement of theorem. Okay? So statement goes as follows: let Y be compact. Okay. Then the projection map phi 1 x cross y to capital X is a closed. Note that Y is compact. This word compactness is extremely necessary. Why? Because counterexample is as follows. I mean that if we consider R cross R toward the first coordinate projection, then this is not a closed map. Why? Because this is R2 cross R2, and this curves is x y is equal to 1, this is x y is equal to 1. If we call this curve C, then pi 1 of C is equal to what? R minus 0, which is open in R. Okay. So that's why this this compactness is very necessary for this theorem. So the thing is that if the second coordinate is compact, the first point projection is always closed to. So this is the fact. Okay, we shall prove in the next session. So using this fact, so there is the following very interesting exercise, namely f sorry. So let f x to y be a map. Okay, let y be compact and Hausdorff. Then f is continuous if and only if graph of f, which is g of f, y inverse x comma fx subset of 1 x comma y so that x belongs to x. Graph x, this thing is closed in x cross y. So the experiment goes as follows: if x to be a map, let x compare y, a y compact and Hausdorff. Then if is continuous, if another graph of it is closed in x cross y. Okay. So from the straightforward direction, that is, assume f is continuous and using that show the graph of is closed. So if we need solve, I mean, in order to solve this direction, you need to use the fact the continuous image of um, sorry, continuous image of compact space form. Okay, and I've got house drop, those things to be used. Okay, so take your time, think about it, how to solve this problem. You need to come up with some map, or you need to construct a new map so that this graph thing comes as the image of this. Okay. Okay, before going this, tell me, so, I mean, okay, so what is the one, I mean, so you know the definition of house droplet, that I understand, but do you know any criteria of space being house drop? Hmm? Okay, so the criteria goes as follows. So one of the important criteria is, I'm sure we have seen this, but possibly different, but whatever it is. Criteria is that a space Y Hausdorff, if and only if it's diagonal, which contains of y comma y, y belongs to y, is a closed subspace. So this is one criteria of a space being Hausdorff. Okay. Now using this criteria, try to show that if continuous implies graph is closed, given y is compact. Think about it. Take your time. Whatever the argument you can think, please tell me.
So using this criteria, we have to show f is continuous or the graph is closed.
Yes, correct. Yes. In order to solve that, you need to. I mean, so the given space y is Hausdorff, right? So in order to
Yes,
solve
yes.
this, that technical thing you need to use that Hausdorff if and only if the diagonal is closed. So you need to use this fact. That's why I mean these are criteria and you need to use it. That's why I wrote
Yes,
it.
yes, sir.
You need to
Okay.
use this diagonal is closed. Then this is you need to use actually. That's why. Now using this and try to construct some map so that image becomes the graph of it and the image becomes continuous. Think about it.
Okay.
Yeah.
Okay. So we can define a like a map in which there are two coordinates f1 and f2.
Hmm.
First will be the, I'm not sure.
Yeah. Uh, yeah. Just repeat again. Repeat again.
Yes, sir.
Repeat the argument again.
So you are saying no, we have to define a map. So
Hmm.
uh, can we define a map like if I call it capital F, it will be a further composition of two maps, one of which is first coordinate is the identity map, second coordinate is F. Not sure.
Okay, that's I mean this will not work actually. So assume f is continuous. So now, I mean we need to define a map definitely. Let's define a map. Yeah. So from map which follows x cross y to y cross. How we are defining map? X comma y goes to fx comma y, right? Now, of course, f is continuous, correct? Nothing to worry about this. Okay. Now, if inverse diagonal of y, this contains all those x comma y belongs to x cross y, such that fx equal to y, correct? And this is basically what? This is a graph of f, right?
Yes, sir.
Yeah. So now the y is given to house drop. So this delta y is a closed house space. F is continuous. So f inverse delta is closed. So that's why g of f is already closed in x cross y. So this is one. So this is one direction. Do you understand?
Yes, sir.
Now, now for the reverse direction, what we can do? Let me just follow me. So for the reverse direction, we need to assume that graph of s closed so that f is continuous, right? So let graph of f is closed. So this much. So we need to show that f is continuous. So what we need to do? So for showing continuity, we need to take a closed subspace, and we need to take inverse. We need to show it is already it is again closed, right? So what I'm taking, let f be closed subset of y. Okay. So we actually need to show that f inverse f is closed, correct? So now, so the now observe something. suppose this is x, this is y, okay, and suppose this is graph of it, okay. Suppose this is our closed f. Now, if we look at this portion, so this portion is what? This portion will be pi to inverse closed f, which is nothing but uh, x cross f, right? Okay, and then this portion is the intersection, and then we are projecting this thing. So this thing will be what? This thing will be pi to inverse f intersection with graph of f, and then we are taking the first coordinate position, right? Now the interesting fact is that this whole thing is nothing but equal to f inverse of f. So sorry, this. So basically, what is this? So we choose first we choose some f, and then we are taking the if pi to inverse f, and we are taking the intersectional graph, and we are taking the first from projection. Then it's coming what? Pi 1 of pi to inverse f intersection graph of f is equal to f inverse f. So this is what we need to show, that this is f inverse f. If we are able to show this, then we are done, because pi to inverse f is already closed, because f is closed, pi to start with the graph is closed by assumption. So this intersection is already closed, correct? Now in our case, y, the second portion of y is compact, correct? So pi 1 is a closed graph. So this is just what we have seen in the previous theorem. So pi 1 of, since y is closed, as y closed, so pi 1 of that thing is also closed. So f inverse f is also closed, correct? So this is the argument. You understand? Only it's left to show that pi 1 of pi inverse of f into the graph of a is equal to f inverse f. I mean, so except this thing, tell me, do you understand the rest of the proof?
Yes.
Now tell me how we will show that pi 1 of pi inverse f into the graph of a is equal to f inverse f. How we will show this? Think about it.
So by taking an element on one side and showing that it or pi number.
Okay. Correct. So yeah, so by doing this, so set theory are when it is possible to do it. So okay, so right now I am not going to prove that. Okay. So yeah, so well, okay. So so these are the following exercises that I thought I will do it in the presentation. So that's the end of the exercise. Okay. So only two or three minutes left. Now tell me, do you have any question or doubt, or do you have any suggestions so that I can put it in that from the next session onwards?
Sir, I'm just very confused with that the initial portion of functional analysis. So if you could get time, because uh, that Banach spaces, the function and derivative on Banach spaces is actually very difficult. So I have many doubts in that particular topic.
Yeah. So just tell me one thing. Just tell me one thing. So do you have any? I mean, have you started this function analysis before, or this is the
Yes,
first time?
yes, sir. Have I?
I mean, have you started this function analysis before, or this is the first time you are starting this function analysis portion?
No, sir. This is my first time. Like I have read this course way back when I did my graduation and post graduation, but I have never taught this subject. But I have interest in the all these courses of related to analysis. So, but functional analysis, I have no idea. So, it's very difficult for me to understand this Banach space and everything. Anything related to non-linear space, actually.
So you don't have any exposure of this function analysis, right?
Yes, sir.
Understand. Okay, no problem. Yeah, okay. So from next session or day after the next session, I'll go through those things. Okay.
Okay, sir.
So apart from that, do you have any query?
Yes, sir.
Apart from that, do you have any query or any suggestion?
No, sir. No, sir. Thank you so much for today's lecture. Thank you.
Okay, thank you. So from the next live session will be on the from the same time next Friday, 7 to 9. Okay. And if you have any question, you can post it on the discussion forum. If I'm able, I mean, I will try to solve it as much as I can. Okay.
Yes, sir.
Yeah. Okay.
So, can I leave the
Yeah,
session?
yeah, yeah. You can leave the session.
Okay, sir. So, thank you so much for today.
Yeah.
Thank you.
Thank you. Bye.
Thank you.